Sorry, I had to step away for a few moments. So welcome back again. And today we're going to continue our study of theories of chemical bonding. And there's a progression here in the things that we've discussed, right? We started out by proposing these Lewis structures. It's a way of just sketching out what the connections of the atoms are in a molecule. And then we added an extra layer, a theory called valence shell electron pair repulsion theory, or VESPER, where we predict, based on the repulsion of the electron clouds of the atoms and lone pairs around the central atom, what kind of shape our molecule is going to have. What we haven't discussed yet is, what is a chemical bond actually? What is happening when two atoms link up to form a chemical bond? And that is the subject of our discussion today. We'll see how far we can get. There's actually two different theories, two competing theories. Each one explains a different aspect of chemical bonding very well, and they are not capable of explaining other aspects. So it's an interesting situation where you have two different theories, each with its pluses and each with its minuses. We're going to go ahead and go to our PowerPoint presentation today, and we're going to pick up where we left off. Lewis theory essentially shows chemical bonds as, single, double, or triple lines. And although we are aware that those do not accurately represent the distance between the atoms in those bonding schemes, it makes it look like, a single bond is a single bond is a single bond. In other words, a single bond between two atoms is pretty much the same regardless of what the atoms are, other than being shorter or longer. The Lewis theory does not account for differences. For example, let's consider hydrogen and fluorine molecules, diatomic gases. I'm going to build a little table here. And we're going to propose, like Lewis said, that the bond consists of the sharing of two electrons between the two atoms, correct? So if we build a little table here, we can compare hydrogen and fluorine, and we immediately see a couple of things. We see that, first of all, the bond dissociation energy, or the bonding enthalpy, is not the same. In other words, these two chemical bonds do not have the same energy. Secondly, but this we had seen already, although they're both single bonds between the two atoms in each molecule, the length of the bonds is different, which makes sense because, of course, we know that hydrogen and fluorine are different size atoms. So when they link together, it makes sense that they'll be a little farther apart. Today, we're going to discuss a theory which is called Valence Bond Theory, or VB. The theory proposes that bonds are formed by the sharing of electrons from overlapping atomic orbitals. So the idea is that the atoms involved in a chemical bond are going to put forth some orbital, or a few orbitals containing electrons, and those orbitals are going to overlap the atomic orbitals of the other atom, kind of like clouds of electron density, sort of like merging into each other. In this case, what we would propose is that for hydrogen, whose electron is in a 1s orbital, the overlap would be between two 1s orbitals. In fluorine, where there's a lone electron in a 2p orbital on each atom, those 2p orbitals would overlap to form the valence covalent bond. And that is the principle of this theory. Now, looking at how a chemical bond forms, and we discussed a little bit of this in that lecture that we kind of skipped over, but you can watch the recorded version of it. Let's say that we're trying to consider, let me get these controls out of the way. Let's say that we're trying to consider two atoms of hydrogen as they approach each other. So in other words, we're going to start here on the right side, and we're going to consider Although the scale shows distance going to the right, we're going to consider what happens as the atoms approach each other. When they are far apart, there is very little chance for one set of electrons to interact with the positive charge of the other atom's nucleus. And so since there is really no interaction, we call that zero energy. There is no, uh, really no relation between the atoms and therefore no opportunity for interaction. As the atoms approach each other, in other words, as this distance decreases, you can see that the electron clouds begin to overlap each other, and a region of greater electron density starts kind of like showing up right between the two of them. Notice that that region of extreme electron density has a maximum where the energy has the minimum. We would say that the reason the energy is decreasing is because as the atoms approach each other, the electrons of one atom have a better opportunity of interacting with the positive charges on the neighboring atom's nucleus. And since that represents a position that favors an attraction, we say that the energy is lower, right? Of course, if you continue getting the atoms closer to each other, you can see where the energy starts increasing again. That is because now you begin to have nucleus repulsion. And nuclear repulsion creates a spike in energy again because you are trying to move the atoms essentially against what is naturally a repulsive force. So you can see where there is a minimum of energy at a distance, and that distance is going to be what we call the bond length. If we were to draw electron density maps, you can see that as the two hydrogen atoms approach each other, there is that region of greater electron density that starts building up right between them. And it has a maximum on the bottom picture there where those electrons are held in a region right between the two nuclei where those interactions can be maximized. Now, the thing is that not all molecules are formed essentially between just two atoms, much less two equal atoms, right? So what would happen if we tried to see the molecule of ammonia? So ammonia is NH3. Let's look at the configuration of nitrogen and do a little orbital diagram here. Of course, we have 1s2, 2s2, 2p3. And as we saw in our study of building up electron configurations, those 3 electrons in the 2p subshell would be localized or be distributed, let's say, mainly in 3 different p orbitals. Now I'm going to bring 3 atoms of hydrogen, each one of those having a single electron in a 1s orbital. So the idea is that if the 1s orbital of each hydrogen can overlap with one of the p orbitals of nitrogen, you would be able, therefore, to increase the stability by putting an electron in each one of these where you can have more stability by pairing the spins. So the next one would be here, and the last one would be there. So this is what valence bond theory initially would predict. Now here's the thing though. Let's think geometrically now. Remember that the bonds, if they form by overlapping p orbitals with the 1s, what would be the molecular geometry? Well, remember, p orbitals are aligned along the x, y, and z axis of three-dimensional space. So if I am going to essentially join this in, right? Guys, I need you guys to come in on time because every time somebody comes in, I get an interruption here on the PowerPoint slides. So I'm going to really encourage you guys in the future, please be punctual, okay? So we can start and we don't get interrupted. Uh, I cannot keep the system from popping these messages and blocking out the slides. So what I'm going to do here is I'm going to put, let's say, one hydrogen atom is going to go here, let's say. I'm trying to get this guy to draw here. It won't draw. Anyway, sorry about that. I can't get this thing to work right now. Here, let's try it again. All right, highlighter. I got a hydrogen there, hydrogen here, hydrogen here. Essentially, that would be 3 atoms forming bonds that are at 90 degrees of each other because these orbitals are at 90 degrees from each other. Well, the actual bond angle, as we saw last time, is 107.3 because the ammonia molecule is not 90 degrees. It's actually built on a tetrahedral arrangement of electron groups, and it gives a trigonal pyramid shape. So how does valence bond theory account for this? Well, here's the proposal. The proposal is that when an atom forms chemical bonds, sometimes what it will do is it'll mix 2 or more of the atomic orbitals to form a new set of hybrid orbitals. This is called hybridization. So what it does is it'll mix at least 2 non-equivalent atomic orbitals. Let's say, for example, one s and one p orbital. These hybrid orbitals that are formed, and essentially when we say mix, what that means is essentially recalculating the wave functions to yield new orbitals, not the original s and p's, but hybrid orbitals with different shapes from the original atomic orbitals. One important thing is that the number of hybrid orbitals you generate has to be equal to the number of atomic orbitals that were used in the process. So now, when an atom is going to form a chemical bond, it has some other options. It can overlap hybrid orbitals on one atom with atomic orbitals on another atom, or you can overlap hybrid orbitals with hybrid orbitals on the other atom. So now you have a few more options to work with here. Okay, now what we're going to do now is we're going to watch a video. We're going to hope that I can make it work here. All right, and it's over here. And before we start, I want to make sure I get these screens out of the way, and hopefully we'll get a good video this time. If not, we'll just re-record it or post it. Here we go.
Chemists use valence bond theory, and especially the concept of orbital hybridization, to answer a fundamental question. How do the shapes of the molecules we observe arise from the orbitals of the isolated ground state atoms that bond? The hybridization concept proposes that in the molecule, the orbitals of the central atom have mixed mathematically and become hybrid atomic orbitals, new wave functions with different electron densities and spatial orientations. Let's begin with the simplest case and see how the theory accounts for a molecule with a linear shape. A key point to note is that the number of atomic orbitals that mix always equals the number of hybrid orbitals that form. Here, 2 different atomic orbitals, one 2s and one 2p, mix mathematically to become 2 identical sp hybrid orbitals, each with one larger and one smaller lobe. The 2 orbitals face in opposite directions in the atom. For clarity, we'll show hybrid orbitals in this simplified form. First, we'll use box diagrams to depict hybridization and consider the central beryllium atom in the linear molecule BeCl2. The isolated Be atom has filled 2s orbital and 3 empty 2p orbitals. In the process of hybridization, the 2s and one of the 2p's mix and form 2 sp hybrid orbitals. The 2 electrons from the 2s become distributed into the sp orbitals, 1 electron each with parallel spin. The 2 other 2p orbitals remain empty and unhybridized. Here is the same process in a box diagram that shows orbital shapes. Putting these ideas together, we can imagine the hybridization process for BeCl2 is something like this. The isolated beryllium atom, with its filled 2s and empty 2p's, is shown with the small box diagram above. The chlorines have 3p orbitals, but will fade out the ones that are not involved in bonding. In the molecule, beryllium has undergone sp hybridization. The half-filled sp hybrid orbitals overlap the half-filled chlorine orbitals to form two BeCl covalent bonds that are 180 degrees apart. From here on, we'll show electrons within orbitals as dots. To account for molecules with a trigonal planar shape, such as boron trifluoride, the model proposes that the ground state boron atom undergoes sp2 hybridization. The filled 2s of the central boron mixes with one half-filled and one empty 2p to become three half-filled sp2 hybrid orbitals. Boron's third 2p remains empty and unhybridized. Here's an orbital depiction of the ground state boron with filled 2s, half-filled 2p, and two empty 2p's. The fluorines have half-filled 2p orbitals. In BF3, the boron atom is hybridized, with the three sp2 hybrids pointing to the corners of an equilateral triangle. Boron and fluorine orbitals overlap to form three BF bonds 120 degrees apart. To account for the millions of molecules with tetrahedral shapes, the model proposes that the central atom undergoes sp3 hybridization. For example, in the carbon of methane, the filled 2s, two half-filled 2p's, and empty 2p mix and become four half-filled sp3 hybrid orbitals. The model describes bonding in methane this way. In the molecule, the carbon's four sp3 hybrid orbitals point to the corners of a tetrahedron. The H orbitals overlap them to form four CH bonds that are 109.5 degrees apart. For other shapes within a given electron group arrangement, the model proposes lone pairs in one or more of the hybrid orbitals. For example, the trigonal pyramidal shape of ammonia arises when the 2s and the three 2p's of the central nitrogen mix and become four sp3 hybrid orbitals, one which is filled with a lone pair. Here we visualize the nitrogen atom undergoing sp3 hybridization. One of the tetrahedrally oriented sp3 hybrids is filled with a lone pair, and the H atoms overlap the other three to form three NH bonds. In the case of water, with its V shape, the model proposes a situation similar to that for ammonia. The 2s orbital of the central O atom mixes with its three 2p's and becomes four sp3 hybrids, but now two of the hybrid orbitals are filled with lone pairs. In the water molecule, the oxygen has undergone sp3 hybridization. Two of the sp3 orbitals are filled with lone pairs, and the H atoms overlap the other two to form two OH bonds. Carbon is most commonly at the center of a tetrahedral grouping of single-bonded atoms. But it also occurs at the center of a trigonal planar grouping that includes a double bond. Consider the carbon-carbon double bond in ethylene. Valence Bond Theory proposes that each carbon undergoes sp2 hybridization. Its filled 2s and two half-filled 2p's mix to become three half-filled sp2 hybrids, and the fourth electron occupies the unhybridized 2p. Let's examine the orbital view and highlight the two ways carbon orbitals overlap to create a double bond. Here, each carbon is undergoing sp2 hybridization. Note how the unhybridized 2p orbitals lie perpendicular to the trigonal plane of sp2 hybrids. The two sp2 orbitals facing each other overlap end to end. The bond they form is called a sigma bond. It is symmetrical along an imaginary line between the nuclei and is not weakened by the rotation of one atom with respect to the other. Now, focus on the two parallel 2p orbitals. By substituting accurate representations of 2p orbitals, you see that they can easily overlap side to side. This results in a pi bond, one that is not symmetrical along the line between the nuclei. Most importantly, it is weakened, and in fact breaks by rotation of one atom with respect to the other. Thus, a double bond consists of one sigma and one pi bond. In the ethylene molecule, 4 H atoms overlap the 4 other carbon sp2 orbitals. Recall that in molecules with more than 4 atoms around the central atom, such as phosphorus pentachloride, the central atom utilizes d orbitals to expand its valence level. Hybridization accounts for the shapes of these molecules as well. In the ground state, phosphorus has a filled 3s orbital, 3 half-filled 3p's, and 5 empty 3d's. In PCl5, the 3s, all the 3p's, and one of the 5 3d orbitals mix to form 5 half-filled sp3d hybrid orbitals. The other 4 3d orbitals remain empty and unhybridized. Here is the ground state phosphorus atom with the 4 3d orbitals that remain unhybridized omitted for easier viewing. We'll move back to see the hybridized p atom in PCl5. The 5 sp3d hybrid orbitals point toward the corners of a trigonal bipyramid, and half-filled 3p orbitals from 5 chlorines overlap them. Sulfur also has an expanded valence level in many of its compounds. In the ground state, it has a filled 3s orbital, 1 filled and 2 half-filled 3p's, and 5 empty 3d's. In the octahedral molecule sulfur hexafluoride, the 3s, all of the 3p, and 2 of the 5 3d orbitals of the central s mix to form 6 half-filled sp3d2 hybrid orbitals. The 3 unhybridized 3d orbitals remain empty. Here you see the isolated sulfur with 3s, 3p, and the 2 3d orbitals that will become hybridized. In SF6, the 6 sp3d2 hybrid orbitals point to the corners of an octahedron, and half-filled 2p orbitals of 6 fluorines have
Oh, I was enjoying that so much. I guess we got cut off a little bit. The video is excellent in displaying how you arrive at these different shapes of these hybrid orbitals and how they account perfectly for the shapes that we predicted in Vesper theory. I don't want you to feel that you have to know all the little details of that process. Okay, so I'm going to come back to our PowerPoint here, and we're going to go back and discuss what are the really important things here, all right? Because I don't want you guys thinking you had to memorize all that stuff that you just saw there. Okay, let's look at the formation, for example, of these so-called sp3 hybrid orbitals. Remember, the hybrid orbitals are going to have different shapes and different orientations than the original atomic orbitals. In this case, 1 s orbital and 3 p orbitals are going to be mixed or hybridized, and you can see in the middle of the picture there the 4 lobed shapes of these hybrid orbitals, which point to the corners of a tetrahedron. And you can see that it even predicts the actual angle, 109.5 degrees between those orbitals. Again, we're showing you pictures. This is done through mathematical recalculations of the wave functions for these electrons. And The origin of saying sp3 is because if you add the quote unquote superscripts, there'll be 1 for s, 3 for p. That means that you combine 1 s orbital and 3 p orbitals, and that should give you a total of 4 of these hybrid orbitals. So when we look at methane on the left or ammonia on the right, what we see is that this sp3 hybridization predicts the tetrahedral geometry. And in this case, the central atom, whether it's carbon or nitrogen, is using purely hybrid orbitals for all the bonds. And in the case of nitrogen, for the lone pair that it has, that is shown here on the top of the picture here on the right. Once more, notice that in the overlap of these orbitals with the s orbitals of hydrogen, you can see the double arrows they're representing 2 electrons that are being held in common, but because they are in a common area or region of space, their spins have to be paired. In other words, they have to have opposite spins. So do I have to know everything that that video showed? No, you don't need to know how and what way do the orbitals combine. All you need to know is the following. Right now, we know how to draw the Lewis structure of a molecule, correct? We've learned that already and we're practicing it. What we're going to do now is we're going to count the number of lone pairs and the number of bonds or atoms bonded to the central atom. We call this the steric number. And essentially, whatever the steric number is, that is how many hybrid orbitals there have to be. So for example, if I have a total of 2 steric number, what that means is I need to combine 2 orbitals. Well, I have only one s. That means that the other one has to be a p orbital. And because there's 2 of them, that means you're going to have these guys in a linear arrangement, 180 degrees apart from each other. Let's say the steric number is 3, which could be 3 single bonds, 2 single bonds and a double bond, 2 single bonds and a lone pair, or a double bond, a single bond and a lone pair, something like that, right? Remember, it doesn't matter whether the bonds are single or double or triple. You count each bonded group as one electron group. So that means that we need, to accommodate this structure, we need 3 hybrid orbitals. So that means we have to combine 3. So that'd be 1s and 2 p orbitals. So that gives you sp2. And you're going to end up with the famous trigonal planar arrangement. Remember, the valence bond theory is not concerned with the actual geometry of the molecules, only of the electron group arrangements. If you have 4 steric number, which again could be 4 single bonds, or it could be 3 single bonds and a lone pair, right, like ammonia, that means you need 4 hybrid orbitals. You're going to combine the s orbital with 3 of the p orbitals, actually all 3 of them, to generate sp3. Again, if you add the superscripts, 1 plus 3 is 4. That's how many hybrid orbitals you're getting. And these are going to point to the corners of a tetrahedral group arrangement. For atoms in the 3rd period and below that can expand beyond the octet, you can have 5 electron groups around that central atom. So now what you're going to do is you're going to recruit, besides the s orbital and all 3 of the p orbitals, you're going to recruit an extra d orbital. And again, that adds up to 5, like 1 plus 3 plus 1. And so this is going to give you the trigonal bipyramidal shape. For 6 electron groups, you will have to recruit then 1 s orbital, 3 p orbitals, and 2 d orbitals. So we call that type of hybrid orbital sp3d2. And essentially, we call the hybrid orbitals by just the acronym of all these orbitals that are getting combined or mixed or hybridized to form it. 6 electron groups is going to give you an octahedral shape, which is exactly what we predicted previously from our VSEPR theory. Okay. So let me, before we move on, let me see if we're going to move back here. to our screen. I want to see if there's any questions. If there are any questions, either post it on the chat room, or if you have any questions you want to ask, you can do the hand raising icon here and let me know. Okay, so what we're going to do is let's take a 10-minute break. Right now it's about 1:45, so we'll reconvene in 10 minutes. And we're going to talk some more about some special situations that are caused when you have, double and triple versus single bonds. All right. So we'll come back in a few minutes. So 10 minutes, please. Thank you. All right. Welcome back. Hope you had a nice little break there. We're going to continue. Today's session will be a little shorter. I'm going to go ahead and put the remainder of the chapter topics on a separate lecture. The reason is it really requires a focused attention, and I don't think that I don't want to be rushed in trying to do it today. So we're going to look at a little more about bonding here. So let's go back to our PowerPoint. Where are we? Here we are. Okay. So let's consider, for example, a carbon atom, which, as we've talked about, is a very versatile element in terms of bonding. On the top, we see the ground state of carbon, 2s2, 2p2. That's the valence shell, essentially, with the 2 electrons in the 2p subshell sitting in separate orbitals. One way of looking at the way that these hybrid orbitals are formed is by pretending that I'm going to take one of the 2s electrons and promote it, meaning put it in a higher subshell in terms of energy, which would be 2p. And now that I have those 4 electrons, I'm going to hybridize a selection of those orbitals. I'm sorry, not hybrid yet, half-filled orbitals. I'm going to make a selection to make the hybrid orbitals. I apologize for that. So I'm going to choose, for this particular case, 3 of those orbitals to make 3 sp2 hybrid orbitals. But that leaves 1 electron by itself in an unhybridized 2p. We're going to choose the Z orientation, which in 3-dimensional space represents, I don't know, what we would think of as the vertical dimension. And let's see what happens when an atom of carbon does this. So here are the electron clouds of these hybrid orbitals. They're the ones that are 120 degrees around, forming like a triangle. And in this picture, they're sort of shaded in a kind of like a green color, but I don't know if that translates well into your screens. And then the single electron in the 2pz, as you can see, is above or below. Remember that these things are waves, and they have areas, regions of higher density with a node in between. So this unhybridized 2pz orbital is perpendicular to the plane of the triangle formed by the 3 hybrid orbitals. So let's see what happens when carbon uses this bonding scheme to make covalent bonds. So let's say that I have not one of these atoms, but 2 of them coming together. The structure of the compound ethylene, C2H4. As you saw in the video, when these come together, each carbon is hybridized to generate 3 of those sp2 orbitals. One of those orbitals on each atom is overlapping a corresponding sp2 orbital on the other atom to form the initial bond here. And we should be able to see it here, right there. Oops. Okay, for some reason, my PowerPoint tools are refusing to work there. That's what I'm talking about, the sp2 orbitals overlapping each other. And notice that the other sp2 hybrid orbitals are the ones that are being used to make the bonds with the hydrogens. So far, you have a trigonal planar geometry on the left trigonal planar on the right. So essentially, this is all happening on the same plane, in this case, from this perspective, as the screen or the paper where you'd be looking at this. Now, let's say that I do a rotation slightly around that carbon-carbon axis so that I can see what is above and below that plane. And we see there these 2pz orbitals, which actually, those clouds, if we depict them accurately, they're not that low. They're actually kind of like reaching out towards each other. And that allows those two electrons to be shared by a single cloud here, and we call that a pi bond. In a pi bond, the electrons that are shared in an electron density cloud above and below the line that connects the two atoms. Notice that if we go through here, the bonds that are right on that line between the atoms, we call them sigma bonds. The electron density is right between the two atoms. This is essentially the initial proposal we made for covalent bonding. Now we're having to amplify to indicate that sometimes you have what are called pi bonds. These are where the electron density above and below the plane of the nuclei of the bonding atoms. So in essence, what we're saying is that when you have a double bond, you have a sigma bond, a pair of electrons held right between the atoms, and a pi bond, in other words, a pair of electrons being held in the regions above and below that axis between the two atoms. Let's look at another possibility. Once more, I take the ground state of carbon there on the top. I promote an electron to generate 4 half-filled orbitals, atomic orbitals. And now this time, I'm going to select to only take 2 of them to make hybrids, which are going to be the sp orbitals. And that means that there's going to be, therefore, 2 unhybridized orbitals, pz and py. In other words, these are going to be perpendicular to each other. Let's look at this other compound called acetylene, C2H2. In this case, you can see on the left how each carbon has an sp hybrid orbital, one pointing towards each other and one pointing towards the hydrogen. But remember that in the structure, if we include those unhybridized p orbitals, you have a pair of z orbitals and a pair of y orbitals at 90-degree angles from each other. And since each one of those contains an electron, 2 electrons can therefore pair up, but they're going to end up pairing up above and to the side of the axis between the atoms. It makes it look like a collection of a sausage with 2 sets of buns in there. Notice that the density cloud is right between the atoms, but also all the way around, indicating a farther kind of dispersion of that electron density. So let's look at a compound that we studied before. This is formaldehyde. We did the Lewis structure of formaldehyde by rejecting another competing structure that generated formal charges. And this is the one that we landed at. Now we're going to try to explain what is the bonding like in here. Again, consider the steric number of the carbon. We have 1, 2, 3 electron groups around the carbon. Remember, the double bond doesn't count as 2, it counts as 1 bonded atom. Since we have 3 electron groups, that means that we should have a trigonal planar geometry. And because there are 3 electron groups, we need 3 hybrid orbitals. So that means that these are going to be sp2. Remember that we said that when you form an sp2 orbital with carbon, you have to leave an electron in a 2pz unhybridized orbital. So here's this monstrosity of a picture here. Now, you might remember about oxygen, right? Remember that the valence structure of oxygen had us at 2s2 2p4, which means that oxygen had in its 3p orbitals, it had 1 that was full and then 2 that were incomplete. So that means that oxygen has these 2 lone pairs. So what it's going to do is, one of those can be used to make the sigma bond with carbon, and the other one can be used, since it's going to be, let's say, for example, that it's using the, let's say this is the X, let's say this is the X axis of the oxygen, and that's the 2px orbital. And so that electron is going to form a sigma bond with the one of the sp2 hybrid orbitals of carbon. The other electron, right, the one that would be in the other, let's say this is the 2pz orbital, that's the one that is above, that one can overlap above the axis between the carbon and oxygen with the unhybridized electron in a p orbital in carbon to form a pi bond. Notice that carbon still has 2 other sp2 hybrid orbitals that are going to form sigma bonds with the hydrogens. So the key thing here is that in the Lewis structure, we see that double bond between carbon and oxygen. Valence bond theory is proposing that that double bond actually consists of a sigma bond, which is an overlap of orbitals right between the 2 atoms, and one pi bond, which is the overlap of electrons in orbitals above and below the plane that is formed by that triangular shape. Cool, huh? I know it's a little challenging because some of us are not as good at translating pictures on a page with 3-dimensional shapes. And I apologize that this looks a little disjointed here. Let me see if I can fix it a little bit here so it'll look a little better. So let me complete this S over there. And this was 2P, and this was that 2 here. All right. Should probably just erase all that. There we go. That's probably a little better. All right. So what we saw was that this would have been the 2 man, P. Wow, that's even worse than before. I apologize for that. My stylus is not very good. I gotta get me a good stylus. Maybe in the break between spring and summer, I'll do that once I get my stimulus check. Okay, but you get the idea, right? So essentially what we're saying is that in the formation of compounds that have multiple bonds, we see that a single bond would represent electrons shared right between the 2 atoms, and that would be 1 sigma bond. A double bond would require us to have electrons that are shared above and below the axis between the atoms, which means you now have 1 sigma bond and 1 pi bond. And a triple bond would require us to have 1 sigma bond and 2 pi bonds. So I'm going to put a structure here for you guys. This is the molecule acetic acid, which is the thing responsible for the acidity of vinegar. And here is the Lewis structure of acetic acid. I'd like for you to come out and tell us, well, I'll let you work on it and then I'll post them. Let's do it that way. How many sigma and how many pi bonds are in total in the whole molecule of acetic acid? I'm going to give you a few seconds to work on it, and then I'll post the answer here. Okay, so let's see. First of all, let's consider all of those single bonds that we have in here. So that's 6 of them, and each single bond is a sigma bond. But We also have a double bond here between this carbon and that oxygen. And each double bond also has one sigma bond as part of it. So that means that we're going to have a total of 7 sigma bonds. Okay, everybody got that right, correct? Okay, let's look at pi bonds. Well, you're only going to have pi bonds where there are double or triple bonds. And in this case, as we saw, we had that double bond there. So that should include 1 pi bond. So the answer to the question, how many sigma and how many pi bonds are in acetic acid? There are 7 sigma bonds and 1 pi bond. Remember, guys, this is theory, okay? All of this is theory. Yes, it is somewhat proven by certain kinds of data that you obtain. But remember that it is theory, okay? Molecules don't form by atoms getting together. Hey, dude, why don't you and I form a sigma and a pi bond? Let's go pi, man. No, it doesn't work that way, okay? Nature doesn't think that it's making these things. We have categorized these things because our brains request that we organize the information around us so we can see patterns and we can predict behaviors, right? That was one of the topics we discussed in our first lecture ever. One more thing that happens when you have double bonds is that you restrict the rotation. So here are 2 compounds, both of which are called, well, actually, this is 1,2-dichloroethane, and the other one's called dichloroethene. So you can see where there's only 1 letter difference in there. The difference is that 1,2-dichloroethane has a single bond. You can look at the Lewis structure there on the top left. Whereas 1,2-dichloroethene actually has a double bond in there. And the point they're making here is that that is going to restrict the rotation around that single bond. What I'd like to do is I'd like for us to go to this video, and I'm going to see if I can find it here. Okay. I'm going to pick it up kind of like after it has started. All I'm going to say is please stay awake. It's a little challenging sometimes to see these things at this time of the day, but since this lecture is going to be recorded, you'll get to see it later if you want. Okay, here we go.
Before we start talking about alkenes and their geometric isomers, I think a good starting point is a simple alkane. This is 1,2-dichloroethane. It's got single bonds between the 2 carbon atoms. And if this was the structure of the molecule, I could draw a picture of it, and it would look, in terms of fully expanded, like the top diagram above. I've got 2 chlorines up top, 2 hydrogens down the bottom, and there's a hydrogen left and a hydrogen right that are slightly obscured because of the geometry. The top diagram is a expanded structural formula. It shows exactly all the bonds in the structure, whereas the bottom one is a condensed structural formula. It still shows us the sequence of all the atoms in the molecule, but it's much, much faster to write. But the thing about this model is that this molecule could be viewed from many different angles, and if I were to view it from, let's say, this angle, I would actually draw the 2 chlorines being left and right, and the hydrogens up and down on each side. It's still the same molecule, just viewed from a slightly different angle, and to show that on paper, I could have drawn those 2 chlorines in 2 different arrangements. It could also sit possibly with the 2 chlorines both looking downwards, in which case I would draw a structural formula like that. Every single one of these are all equivalent because it's still the same thing, just viewed from different angles. But there's one more trick that this molecule can do, and that is that whenever there's a single bond present, the atoms on each end of it can rotate about the axis of that bond. That means that this one here can spin on this axis of the double bond, and this one here can also do the same. Okay, so both of these atoms have this free movement available. They can spin around as they wish, and that means that I don't necessarily have to have the two chlorines sticking up side by side. They could be in any other possible position relative to each other. So it means that this molecule could also be drawn like this, in which case there is a chlorine above and below on each side, and the hydrogens are taking up the other remaining spots. It's still the exact same molecule, because all I've done to change it from what it was originally to what it is now is just rotated the molecule internally within its own structure. The same thing would apply for any simple single bonded carbon chain. This is 4 carbons all in a line, but I don't necessarily have to draw them like that, because with all of these bonds having free rotation, I could draw 3 in a row and 1 down, or I could draw 1 up and 1 down, or I could draw the whole thing as some sort of N shape or as some sort of U shape. Exactly which one I draw is really irrelevant, because it's all the same molecule, just twisted internally. Of course, for clarity, structural formula will generally have all atoms drawn in a row, or if you draw the skeletal formulas, generally it will be drawn as a bit of a zigzag. Alkenes are different because they have a double bond between the carbon atoms, and that limits what kind of rotation is available for those atoms. But first of all, if we looked at this one here, it's 1,2-dichlorobutene, and I could hold this in a couple of different positions to give different perspectives. So this one here probably matches this. Yes, it does. So on the left we've got the chlorine up top, and on the right we've got the chlorine down the bottom. Okay, but the exact same molecule flipped over, we could now draw it as having a chlorine on one side down on the left, and on the right hand side it's now up. It's still the exact same molecule, just one perspective versus another one. However, what this molecule can't do is rotate on the axis of this double bond. That means the 2 carbons on the end of that double bond cannot twist, spin independently of the other one. The double bond does not allow it. There is no ability to twist it around. That means that I can't get this structure twisted around and get both my chlorine atoms facing either both up or both down. So at no stage can I turn this structure into this one. They both still have the same structural formula, because in terms of the sequence of atoms in the molecule, it has got a hydrogen and a chlorine on the left and a hydrogen and a chlorine on the right. There's a double bond between them, so in terms of the sequence of atoms and bonds it's identical. However, the arrangement of space of these atoms is different.
Okay, wake up. We're back. Yeah, I think that's pretty much enough. You get the idea, right? When you have a single bond between atoms, you are able to rotate freely, and you can generate a lot of what seem to be like different shapes, different organizations, but they're not, they're all the same. All the atoms are connected the same way. But when you have a double bond, things change. Let me show you back to our PowerPoint show here. The thing is that this is kind of a little complicated, but you can look at it later on. I think this picture is in your TRO book. And let's get that out of the way here. What I do want to show you is the next slide here, because that one shows you exactly what we're talking about. If instead of the Lewis structures in the top, we did the space filling models that you have in the bottom, you can see how the presence of the double bond does not allow rotation around that carbon-carbon axis. And therefore, the structure on the left and the structure on the right cannot be converted into each other neither by kind of putting the molecule, looking at it from a different perspective, or trying to rotate around that carbon-carbon bond, because you can't anymore. And therefore, these two compounds have the same formula. They have the same atom-to-atom connections, but they have different orientations in space. We call these geometric isomers. Isomer means compounds that have the same formula but different structure. In this case, the difference in structure is geometric. It has to do with how they're oriented in space. And the traditional nomenclature of these kind of things is to call the compound where uh, if you go from left to right through the double bond, coming in from the left, you're entering from the bottom, going across the double bond, you're exiting from the bottom also on the same side, in other words, as the double bond. We call that the cis isomer. And the one on the right, where you enter the double bond left to right, and then you exit on the opposite side, we call that the trans uh, isomer. You'll get to learn more about these kind of things in your organic chemistry later on. And you will see that these compounds, that small difference makes a huge difference in many of their properties. Like, for example, their polarity, their boiling points, their ability to mix with other compounds, et cetera, et cetera. Okay, let me finish up by pointing out that, again, we are talking about something that is a theory. It is a model. And of course, it's going to have some limitations. The first one is, we already talked about this, just like Lewis theory, Valence bond theory cannot explain molecules like nitrogen monoxide, because it cannot explain how you would have a stable molecule when you have electrons that are not paired. Valence bond theory as well as Lewis theory kind of require that electrons be paired up. The other thing is perhaps a little more interesting, and it is that valence bond theory does not address the magnetic properties of substances. Consider the oxygen molecule. The oxygen molecule, if you count the number of electrons, you can see that it's an even number. In other words, there are no unpaired electrons. Every single electron is paired. And by pairing, we mean that for every electron of a spin up, there's a corresponding electron of a spin down. That's what it means to be paired up. It means that you have all of the spins are canceled out. That means that this molecule should have no net magnetic field generated. It should be diamagnetic. Now, here's what's interesting. If you run liquefied oxygen through a magnet, look what happens in the middle there. It sticks. In other words, oxygen molecules do have a magnetic field. They are paramagnetic. But according to the Lewis structure and according to Valence bond theory, all of the electrons should be paired up, and therefore there should be no net magnetic field. So this is where the valence bond theory falls short. You can actually test for this by running this experiment. I think I mentioned this earlier. This is just a sketch, okay? The machine doesn't look like this, but it's kind of a sketch. You're basically gonna suspend a tube with your sample from a balance, and you're gonna bring it close to an electromagnet. If the substance is paramagnetic, in other words, if it has unpaired electron spins and therefore has a net magnetic field, it is going to be drawn into the electromagnet. And based on the weight that is pulled on the balance, you can do classical physics calculations as to the strength of that magnetic field, and even calculate pretty much how many unpaired electrons are in that structure. So this is the experiment that we do. So because valence bond theory is great at explaining the shapes of molecules and fits the Vesper theory, but it cannot explain the magnetic properties of substances, it is time for a new theory, and this is called the molecular orbital theory. However, we're going to leave it here. I am going to cover that in a separate lecture that I'll record, and you guys will get to watch. I'll put the announcement out there. so you guys can get to see it, okay?